In our last video, we went over the terminology related to local mins, local maxes, and saddle points. In this video, we're going to go over the second derivative test for local extreme values so that we can find the mins, maxes, and saddle points. The second derivative test for local extreme values. Suppose that f of xy and its first and second partials are continuous throughout a disk centered at a comma b, and that the partial derivatives, the first partial derivatives evaluated at AB are identically zero. And again, another way of thinking about this is a claim that the gradient vector at AB is equal to 0. 1. F has a local maximum at the point AB if the second partial with respect to x is less than 0. Second partial, think second derivative, and think concavity. When I had a second derivative that was less than 0, I got a curve that made a concave down shape, putting any critical point at the top, looking like a local max. So this is a claim about concave downward. And fxx times fyy minus fyx fxy. So this is a algebraic combination of all of the second partials, the non-mixed second partials and the mixed second partials. Now, one thing you should be aware of, I like writing this calculation down exactly like this, but because my function and all of its partials that I'm considering are continuous, these are equal to each other. So a lot of times you'll see this calculation written down instead of with both mixed partials, with one of them squared. And of course that's the same statement. I simply like writing it down the other way, like this. Okay, so the second derivative, or better said, the second partial with respect to x is less than 0 is not a guarantee that if I looked at every path, I'd get a concave down shape. But if I put it together with this calculation, fxx times fyy minus fxy times fyx bigger than 0, that actually does guarantee now that all of my second partials behave the same way, that I always get that concave down shape. So I have a spot where the gradient's equal to 0, and I always have that same concave down shape, telling me there's a local max at that point. So the local max would happen at a comma b. And that's the way to think about this. This is a claim about a second derivative along a particular path, this in particular where we've frozen y as a constant and have taken the derivative with respect to x twice. This checks to make sure that all of my second derivatives are going to behave the same way. When this calculation comes out positive, then this is all I need to know. Come down to the second bullet point. F has a local minimum at AB if fxx is bigger than 0 and fxx times fyy minus the product of the mixed partials is bigger than 0. So again, think about this like concavity. If you freeze y equals y naught, and take two derivatives with respect to x and get a positive, that's making a concave up shape along that path. So anywhere where the derivative would be equal to 0 would be at the bottom, that critical point. This checks to make sure all of my second partials are behaving the same way. So any path would look like that, making sure that's a local minimum. Okay, if this calculation, the product of my non-mixed second partials minus the product of my mixed second partials is less than 0, that's where I have a saddle point. When this calculation comes out less than 0, it's telling me that along some paths I have a concave up shape, and along some paths I have a concave down shape, giving me that saddle point. So when I look through this calculation is repeated 3 times, bigger than 0 in these two, less than 0, and that seems like I'm missing one because there's actually a fourth statement. If this calculation works out to be exactly 0, then the test is inconclusive. We actually can't conclude anything. There might be a min, there might be a max, there might be a saddle point, there might be nothing. We have no idea when that happens. We have to investigate it using other methods. All right, let's work through an example where we get to use the second derivative test. But before we do that, I want to talk about this calculation just a little bit more. this algebraic expression involving all of the second order partials is called the discriminant. Sometimes you'll see it referred to as the Hessian. And it actually can be thought of as coming from a determinant. Where I put in all of my second order partials. And so what I can do is organize it by row and column. So I can think about this row as being the first derivative I take would be x, so I have an x and an x. This row would be a y and a y, and then I do that again in columns. So this spot I take a derivative with respect to x and then x again. And this spot I take a derivative with respect to y and then x, and so on. And when I take that determinant, I get out the discriminant. So we might call it the discriminant, we might call it the Hessian. It's really convenient to have a name for it because it's quite the thing to write all out. Okay, so let's do an example. Consider f of xy equals x squared minus y squared. Find all extreme values and saddle points. Well, this is a good example to start off with because it's not a complicated function to deal with, and we know the answer. Right, we know this is our hyperbolic paraboloid, and we know there's a lone saddle point at the origin, and that's all I'm going to find here. There's no other local extreme values to find. So, if I think about the second derivative test for local extreme values, I need to calculate the first partials, and I need to calculate all of the second order partials. I'll need to find any critical points, which means both of these are, which either means both of my first order partials are equal to 0, or one or both of them doesn't exist. These are both polynomial expressions, so I know the only critical point I will have is where they're both equal to 0. So I need 2x to be equal to 0, and I need minus 2y to be equal to 0, which means x is 0 and y is 0. So my only critical point is at the origin. Okay, well, one thing to remember is that sometimes when I take partial derivatives, these might be functions on both x and y. When I set them both equal to 0, that actually gives me a system of equations to solve. There'll be a system of equations on two variables. Solving that system will give us our critical points. All right, let's write down our second order partials and then see if we can find the value of the discriminant evaluated at that critical point. So the non-mixed second order partial is easy to calculate. fxy, well, I need to take the derivative of this with respect to y, I'd get 0. And that's all I need, right? Because in the calculation for the Hessian, the discriminant, I really only need one of them because Clairaut's theorem tells me they'll be the same, but it's not too hard to take the derivative of that with respect to x and also get 0. So for every point xy, our discriminant is equal to minus 4. So our critical point of 0, 0 we can summarize in a table. Here's my critical point. I'm going to write down the value of fxx at 0, 0. Well, fxx at 0, 0 is 2. The discriminant's value is minus 4. Going back to the second derivative test for local extreme values, this is all I needed to know. I went down and wrote f(x)(x) because, well, in the other two cases that I care about for this problem, if it's less than 0 and this was positive, I would have a conclusion. And same thing for this. But the discriminant is less than 0, so I know there's a saddle point. And that saddle point is the point 0, 0, and I plug 0, 0 into my function and I get out 0. And there I have it formally, why I have a saddle point on my hyperbolic paraboloid at the origin.